Next, or the kind of last presentation before we hit the flash presentations, comes from Hikaru. Hikaru is a research associate that's been working with us for 5 years. Hikaru is lead modeler on our MMIC Grand Challenge project interactions with those guys out towards Glasgow Airport, and I'll be talking a little bit modeling and development processes for continuous direct compression. Cheers, Hikaru.
Yeah, thanks you for the introduction. So, as you've heard from many of our speakers over the course of Open Day so far, there is obviously great benefit in companies coming together, pooling their efforts and collaborating on research and various projects, pooling their efforts and of course our funds and manpower as well. So obviously I'm going to specifically focus on sort of continuous direct compaction or compression models, but this work is part of the Medicines Manufacturing Innovation Center. So obviously all the details are up here. So it's owned and sort of run by CPI, Centre for Process Innovation, and it's being set up just outside of Glasgow, in fact. I've put like a little handy schematic there. I've been told it looks like EastEnders. That wasn't my intention, but you know, follow that little map. So the University of Strathclyde is an academic partner. There are sort of founding industry partners, AstraZeneca and GSK. It's also being funded by the sort of Scottish Government, UKRI, Scottish Enterprise. There are also, Pfizer have joined as well as a sort of DFE, Gericke, Applied Materials, Siemens. So there's lots of partners from various backgrounds collaborating in the MMIC. So if you have to try and summarize the overall goal of MMIC, it's to kind of develop a state-of-the-art pharma R&D center in Scotland, and there are sort of various sort of parallel research activities that are occurring here. So I'm going to sort of preach to the choir a little bit, but I just want to kind of go over sort of process models and digital twins and what they are, and I guess also kind of what they're not. So obviously we do many physical experiments. We've heard from many speakers today about the need to do comprehensive design of experiments to kind of capture the design space and operating space of various sort of phenomena and experiments. But of course, these can often be very material, time, and sort of labor intensive. So if we had a way to know in advance, or at least have a good guess as to what might happen in advance, this can sort of speed up research down the line. So what a digital twin, now if you ask 10 different people, you might get 10 different answers as to what a digital twin is. But the way I see it and the way how a lot of my colleagues see it is obviously it's a digital virtual representation of your real system. And in lieu of doing extensive design of experiments in reality to narrow down where you'd want to be, you'd have a model that will, to a degree, do that for you and give you a good idea of this is where you likely want to be, so you can then do more targeted experiments. And so I'm going to be talking to you about a digital twin of a CDC process, so continuous direct compaction. Now, obviously, continuous direct compaction is an entire process, a whole flow sheet. Obviously, this is a very simplified version that you have up here. Obviously, you've got feeders, blender, tablet press. Again, very simplified. There are other aspects involved here. And of course, various sort of models or modeling efforts that are involved in capturing what happens in each of these. Obviously, in feeders, you need to be able to know how they feed, what kind of mass flow performance you're getting. For the blenders, obviously, macro mixing, resin time distribution models, micro mixing as well. What's your content uniformity? How well are the tablets that you then produce? How well are they lubricated? What's the impact on tableting performance? And a lot of my colleagues are working on various aspects of these. Unfortunately, I don't have time to talk about everything today. If you go around some of my colleagues' posters, we kind of range between posters 42 to kind of 60. We're kind of spread out in between there. If you can come find us, we can cover some of these other aspects. But I'll be talking to you about, I'm not sure if I have a laser pointer here, but I'll be talking to you about feed factor prediction. So feed factor, in essence, is basically how much mass flow you get coming out of your feeders. Now, I'm sure many of you will be familiar with what a feeder is, but for those of you who aren't, a feeder is essentially a drum of material, and underneath you've got a screw. As the screw turns, it kind of drags material out, and you get powder going to wherever you need it to go. So I've got a wee schematic of a feeder up there. So as I mentioned, as the screws turn, material comes out. Now, of course, in a batch process, you could have, if it's possible, have an operator filling in more material as necessary. But in a continuous process, obviously you have to have very good control over how much mass flow you're getting, and of course the variability in that mass flow as well, although I'll be specifically talking about the magnitude of the mass flow. I've got a wee diagram here of obviously a very idealized modeling depiction of the kind of mass flow you get. But this is an equation that's quite commonly used in literature. So this describes the feed factor. So obviously mass flow is typically mass per unit of time. But for here, we're using mass per turn of the screw. So one revolution of the screw, a certain amount of volume will be pushed, and how much mass do you get from that? Now, depending on what kind of a powder you have, you can get varying performance in this feed factor, and that's kind of described in the various sort of colored curves you have there. Now, I'll focus on these sort of one at a time, because obviously there's quite a few things going on. If you look at the red curve, that's a beta value, which is one of the model parameters of 50. This means that you have very sort of stable feed factor for quite a long time. This is plotted against hopper fill fraction. So as your hopper is emptying of material is being dragged out, even though it's getting emptier and emptier, you're still getting pretty stable mass flow. And then obviously as you run out of material, it stops. The other curves here have lower values of this beta parameter, but what's happening in reality is that even from quite early on, even though you're still relatively full in terms of your hopper, your mass flow is already starting to decrease. Not by much perhaps, but it starts sooner. So, and knowing what kind of behavior you're likely to get when you're doing these runs kind of informs you as to how your feeder should operate. If your mass flow goes down like this, or if your feed factor goes down like this, your screw can speed up to still maintain the same per time mass flow. But of course, feeders all have minimum and maximum screw speeds. These are specific to the equipment. So knowing what this performance trend looks like can inform you as to how your feeder should operate, and even whether your feeder can operate at the level you need it to. So what we've done here is, now before I go into the specific plots here, obviously powders going down emptying down a hopper, filling into a screw, the screw is spinning. Inside the hopper there is a agitator as well that is trying to ensure that this material fills into the screws as much as possible. There's quite a few things going on, quite a complex system, although it's essentially pure material in a bucket with a screw. So modeling the kind of phenomena and mixing patterns and flow patterns that happen here can be quite complicated. Now, we've heard from a lot of great speakers about looking into really small detail, molecular simulations, real mechanistic models of, really granular detail. Here we're going completely the opposite direction, and we're taking a very black box empirical approach and applying machine learning to see what trends we can identify. So obviously you do have to do some experimentation in advance. So my colleagues, we generated lots of feeder runs. So filled feeders up with material, let them run to empty, and then kind of measure what kind of mass flow we were getting. My colleagues did this across lots of different materials, various different feeders, each with their own sets of screws, and measured what kind of performance we were getting. And when it comes to the equation itself, which I've got up in the corner there, there's the FF max, which is essentially what's the kind of magnitude of mass flow or feed factor that you're getting. Am I getting 2 grams per revolution? Am I getting 1 gram per revolution? And the other parameter, beta, is how quickly does that decay. I'm only going to focus on one parameter here, FF max, due to time. But what you see up here is training and testing for the machine learning models for the FF max parameter. Obviously, I've kind of obscured things a little bit here because we've got some proprietary API data. But on the left, you see blue, which is excipients and APIs, mainly excipients, that my colleagues kind of generated for this. So these are actually observed model parameters that we gained from looking at the raw data. The green is similar, although this was provided kindly by Pfizer. So this was published in a Pfizer research paper for a different project, but a lot of the metadata aligned, so we were able to include this. And the dashed lines that you see here are kind of accuracy targets specified to us by partners. Obviously, models are only as useful if they are accurate, but obviously you have to kind of specify in advance what those targets are. So these are plus or minus a certain percentage of the feed factor that you want to kind of gauge how close are we to where we want to be. Obviously, when it comes to training, as one would hope, obviously that is relatively straightforward. Obviously, it's the training, it's kind of meant to be. And you can see here most of the data points do fall within the accuracy thresholds, although of course there are some that are outside. We can't get a perfect model. What we do want to highlight here is that you can see that some of the data points are a lot fainter than the other ones. Obviously, you've got solid data points, the ones that are slightly paler. The paler ones are the true data points. Those are sort of replicates. In some cases, we had 2 or 3 runs per feeder screw material condition. For others, we had 6, 7, 8 data points for that given condition, either true replicates or different RPMs. And in some cases, there was a degree of variability in these, even though ostensibly it's the same material in the same feeder with the same equipment. Now, if you've got results that are substantially different for what should be the same thing, a machine learning model can struggle with that sometimes. So we've taken like the average, for these replicates to use in the training, although they were weighted with how many data points we originally had. So that's the explanation of the faint and solid data points. When it comes to testing the model, obviously we kept some data separate to kind of gauge how well our model is actually performing. So again, these are a mix of, on the right here, excipients and APIs. And one thing I did forget to mention, the inputs to this machine learning model are sort of the various material properties you would get for these substances. So kind of measured in a particle size, densities, FT4 measurements, Brookfield measurements. And we combine these with the various properties of the kit itself. So what's the pitch of your screw, what's the diameter of your screws, how big is your hopper. So we're trying to kind of tease out from the data that we see how these link to the properties of what you're putting in there and the properties of the kit itself. Now on the right, as I said, testing data points for various APIs and excipients. Most of them do fall within the accuracy thresholds, so that's good. Obviously, you can see some red and blue data points here. The difference here is that I wanted to see what the impact would be if I'm missing some of my inputs. Now, in an ideal world, you would have access to all the data that you need. You can measure everything that you want to measure. You have access to all the kit you need for your measurements. But either you don't have enough material to do all the material characterizations you want. Perhaps your colleagues come from API development and say, here's 300 grams of this new substance. Go away, do what you need to do with it. That might not be enough to do all your tests. Or it's historical data, and at the time, for the purposes of that project, not everything was measured that you need. Perfectly plausible. How would the model perform if some things were missing? So I kind of removed some predictors to see what the impact would be. And you do see some shift. But in general, if you're originally within the accuracy targets, you will still remain within the accuracy targets with some exceptions. If you start outside, you're typically still outside. So kind of zooming back out a bit now, so I kind of covered specifically a CDC model flow sheet, but even within that, just for the feeder modeling, how does that kind of fit into the work as a whole, or the digital twin as a whole? And Tabasin kindly took us through the need to have sort of a systematic way to measure data and store metadata. So that kind of thought process kind of comes into play here as well. So kind of how we see this fitting into the efforts at MMIC as a whole. Obviously, it's quite a complex graph you have up here, but essentially, once you've got your machine learning models and your flow sheet set up, integrated with various software, there will be a systematic way and workflow in place to gather new process data or measure new equipment data, and that will get stored in a database. If you measure a new material property, again, obviously measure those, do the characterizations in a standard way, label that data and store it in a systematic way alongside all the historical data that you have, so that when you're actually using your final product, all the data is easily accessible and can be integrated with very little effort. And once you've done some of these calculations, if you have parameters and results that you need to store, again, store these in a systematic way in databases as well to allow, obviously, efficient or further use down the line by subsequent users. So obviously this is, again, a big group effort. So the research is being funded by MMIC and through them the sort of Scottish Government, as I mentioned, UKRI, Innovate UK. Again, partners, Gary K, AZ, Pfizer, DFE, Applied Materials, Siemens, Perceptive Engineering, of course, now, Applied Materials. So this is a big collaborative effort. I have many colleagues. Many of them have posters out there as well, so please, come speak to us. Kind of over time a little bit, so I'll try and end here. Thank you for listening, and I'll take any questions.
Thanks, Hikaru. Do we have any questions at all? Got a quick one for you. Oh, sorry. On you go, Andy. Get you a mic. Just a sec.
might be a very quick question, but when you're removing some of the parameters from the test set that you're doing, is it consistent, what you're removing from, are you removing the same thing from each point, or are you randomizing that?
Are you talking about when I was removing certain input predictors to kind of see? Yeah. So on the plot on the right, the same input was removed from each case to kind of gauge what the impact would be. As part of this analysis, I removed various combinations of inputs, some wholesale from, okay, if we didn't have FT4 data, what would be the impact? Or if we just didn't have tap density, for example, what would be the impact? I don't remember specifically what this exact plot is, but I looked at various ways or various combinations of removing inputs. Obviously, some have more impact than others. There are some inputs that are key, and if you don't have that, it's not really going to work. But for many of them, there are sort of varying degrees of impact. Obviously, as many machine learning models will have a ranked importance of what it thinks is important based on what it saw as data. But in this case, in this plot you see here, the same thing has been removed, a single input from each case.
Cool. Thank you.
Any other questions? Jump in with one. So you've trained the model there on different feeder and sort of configurations and so on. Have you tried to use that model to predict for, unseen configurations or unseen bits of equipment to check how it performs, with stuff it hasn't seen before, effectively?
So technically, yes. So this specific results that you're seeing up here focuses on sort of two feeders, a GA compact feeder and a Gary K222 feeder, for those of you who may know what those are. We also have data for 1, 2, 3 other feeders with various screws each. What we have looked at is for when we were originally sort of collecting the data, there were occasionally some screws that weren't included in the original sort of data gathering effort. So we have the data for the various sort of feeders, but in some cases, we've got data for screws A and B, but not for C. So we have explored how it performs for this mystery screw, and it's kind of variable. It does depend a lot. I haven't had time to include that in here, but we haven't looked at an entirely different feeder. We have explored for either those feeders, but different screws. So it's kind of yes with a caveat.
No, more data and you'll get to that, I'm sure. No, good stuff. Okay, well, thanks, Hikaru. That was great.
Thank you.